Didn't we just finish saying that the electric field in a light wave is the speed of light times the magnetic field? Now, to me, that means that we could define the speed of light like this. Not only could we define the speed of light as the electric field divided by the magnetic field, but it also seems to indicate that the electric field is really big compared to the magnetic field. And in particular, the magnetic field is the electric field, however big that is, divided by the speed of light, which is a relatively enormous number. So the magnetic field is much smaller than the electric field. However, it has the same energy contribution. When I was a kid, my mom, excuse me, my mom used to always say to me that intensity is power over time. And so I began to believe her, and then I did a couple expansions on that, and I said that power, well, certainly power is change in energy divided by, oh man, change, what the heck? My mom never said this. She said it was power over area, right? And then I'm going to say, there, that's where our A is supposed to be. Yeah, we're going to divide by area and divide by time for change in energy. Okay, sorry about that. But the problem is, of course, this is a capital U, and we know that the change in energy is going to be, naturally, it'll be the volume times the change in energy density. That is, that tiny little guy right there is energy per volume. And I want you to consider the following situation. Today is, in fact, Valentine's Day, and I'd like you to consider a very small potted plant. It is, well, it's the beginning of a redbud tree, and the redbud tree is all like this for love, and there's a flashlight over here, or shout out to England, it's an electric torch, and it's doing this. It is on, and it is shining a light at the potted plant. What color should light be? Orange. Okay, so light's coming out of the electric torch and hitting the potted plant so that it can photosynthesize and grow, etc. This distance here, delta x, between the light and the plant, well, that's going to be the speed of light times the time that it takes for the light to get over there. That's what delta x means. I mean, I guess this is sort of defining the speed of light. And also, we've got some area defined for this leaf. Probably do it in a circle, make it a little bit easier for our electric torch, but let's say that we can shine a light on here, and I'm interested in the volume of energy that is going to be hitting the leaf in some amount of time. The volume of energy is simply the area of this column of light times the distance that that light travels in some amount of time. So the volume in that amount of time is simply AC delta T, or a cat. Okay, well, that's a little bit interesting. Now, let's take all of this business back up into here. My plan now is to say that we've got, instead of energy change, we've got energy density change times the volume of light, which is a cat, and then we're supposed to divide this still by area and time. And are you thinking what I'm thinking? Yep, wonderful. That and that and that and that, and we've suddenly just got energy density times the speed of light. That's what the intensity of light is. It's the energy density of the light times the speed of light. We've already studied the energy density of light waves, so we can just multiply what we had previously by the speed of light. That gives us 1/2 the speed of light times epsilon naught electric field square plus 1/2, I mean, I guess I'll put the mu naught down here, the speed of light times the magnetic field square. But remember, their contributions are equal. I think we've even said that in this particular video. So that would be the same thing as C times the permittivity of free space times the electric field square. And that, of course, is the same thing as C over mu naught times the magnetic field square. All right, fair enough. Okay, and I want you to look at this. Each of these is very much like, wait a second, you see the analogy between electromagnetic fields and kinetic and potential energy? You remember that the energy of an oscillator, energy of a simple harmonic oscillator, you could write that as 1/2 mv max square, and you could also say that it's the same thing as 1/2 k times the amplitude squared. Look at this. We're squaring amplitudes, we're squaring speeds. I don't care which one you see as the other, but we're always squaring stuff or multiplying by this thing, and usually there's a half and all this nonsense. Unbelievable. It's just so beautiful. If we're looking for average intensity, though, we have to be a little bit more careful. We'll go purple with that, like our electric torch. Here we go. We'll go purple, and we'll say that average intensity is the speed of light times the average energy density. All right, and we probably need to use RMS values for the electric field and the magnetic field. These are going to be maximum values, or instantaneous values as well, but really these ought to be averages. Yeah, put some averages in there. Okay. The other beautiful thing about light, not only does it carry energy with it, it's also got momentum. When I first learned about momentum, they told me that P is m times v. So I know you're pissed right now because light doesn't have mass. Sorry, light still carries momentum. So we're going to modify this sucker. Modify. In particular, I'm just going to state that the momentum of light is its energy divided by the speed of light. Let's just see if the units work out. This momentum here, the units of that are supposed to be kilograms times meters per second. And the units of this energy, well, I guess that's going to be joules. And I'm supposed to divide that by meters per second. So I'm going to do joule seconds divided by meters. Let's expand a joule. I think a joule is a kilogram meter per second squared. And then I'm supposed to take this and multiply it by seconds and divide it by meters. Let's see what happens. If we, joule, meter, kilogram, meter per, oh no! A joule is a kilogram meter squared per second squared, because a newton is a kilogram meter per second. So now we can clean everything up and it will work. This cancels that and this cancels that, and we do in fact find that this is at least a reasonable definition of momentum because the units are consistent. We're going to take kilograms and multiply them by meters per second. So let's work with this definition of momentum and see what it gets us. I know you don't trust it, I know you don't like it, but I want you to consider that electric torch we had. Remember that thing was sending light? Let's call it a flashlight. Let's be honest with each other. It's a flashlight. Come on, really? It's sending light over here, and the light is hitting, I don't know, your pretty face. Yay! I think I'm glad that you have bangs because they look very good on you. And the light is hitting you, and, ooh, spiking your hair today. Very nice. The light is hitting you, and the energy that's plopped on your face during some amount of time is this. Let's say the energy is equal to, well, the average energy density. This is a lowercase u. This is an uppercase u. Can you even tell? I don't know. The energy that's plopped in your face is that average energy density times a cat. Cool. This is the volume of light that will be hitting you. That distance is the speed of light times t, and this is the area of your face right there. And then I'm gonna say that the impulse, wait a second. You know how impulse relates to change in momentum? Why, it's exactly the same thing. Where are we going here? Pink? We're going pink. I'm gonna say that the impulse during some amount of time is the average, wait a second, impulse relates to energy. Oh, I'm just gonna say this is the change during some amount of time. I'm just gonna plug that sucker in. Average energy density times a cat. And then I'm supposed to divide that by c, by this equation right here. I just plugged in what u is. I'm taking this and plugging it in right here. And then I'm gonna go, wait a second. Here's what I'm gonna do. I'm actually, although you know I want to cancel those c's, I'm not going to do it because I remember an equation for average intensity. The average intensity equation was u average times the speed of light. So I'm going to plug that in right here instead. And I'm going to say that this is the same thing as average intensity times area times delta t. We don't get to say anything cool like a cat or anything, but it's still divided by c. And wait, whoa. Do you remember how force is related to change in momentum or impulse? Well, of course, average force is change in momentum divided by change in time. Here we go. I know that this, wait, I'm supposed to take this and divide it by time? Well, that's obviously average intensity times area times time divided by c and time. And now I'll cancel out some times. This is average intensity times area divided by the speed of light. Okay, awesome. And wait a second, is that right? Yeah, that's right. Now, let's continue, and we can say that this, wait a second, isn't this related to that? It definitely is. Let's go instead to average energy density times area. Force! The force of light is the average energy density of that light times the area. But wait, isn't there supposed to be a speed of light in here somewhere? No, I think it's cool. But check this out. Pressure. Don't confuse pressure with momentum. This is a lowercase p. Pressure, uppercase P, is force over area. Force over area. There must be a problem here. What the heck happened here? Change in momentum is this business right here, and I said that this is U average times C, so it's U average times area. That's lovely. That's absolutely lovely. And I'm going to say the pressure is force per area, so it's going to be, wait a second, it's going to be this, I'm going to take this definition right here of the force and divide it by area, and I will find that the pressure of light is the average intensity of the light divided by the speed of the light. Speed of light's always going to be the same, so if I want more light pressure, I need to get a greater average intensity. And intensity has something to do with the area, so I guess I can increase the average force if I have a much greater area, so I can sail through space with an enormous sail pointed at the sun, and it'll push me away from the sun. Yay! This is called radiation pressure. It's one of the major reasons why the sun is losing an enormous amount of mass. Let's say a tiny little bit of stuff plops away from the sun, I don't know, a hot hydrogen molecule or atom or something, and it's, yeah, right, a molecule of that temperature. So it's over here, and it just gets hit by the sun, and then suddenly the light from the sun is hitting it, and it's causing it to move away. It's even greater than the gravity for very small particles. That's about all I have to say about that. And then I'm going to say, there, that's where our A is supposed to be. Yeah, we're going to divide by area and divide by time for change in energy. Okay, sorry about that. But the problem is, of course, this is a capital U, and we know, but it also seems to indicate that the electric field is really big compared to the magnetic field. And in particular, the magnetic field is the electric field, however big that is, divided by the speed of light, which is a relatively enormous number. So the magnetic field is much smaller than the electric field. However, it has the same energy contribution. When I was a kid, my mom, excuse me, my mom used to always say to me that intensity is power over time. And so I began to believe her, and then I did a couple expansions on that, and I said that power, well, certainly power is change in energy divided by, oh man, change, what the heck? My mom never said this. She said it was power over area, right? Didn't we just finish saying that the electric field in a light wave is the speed of light times the magnetic field? Now, to me, that means that we could define the speed of light like this. Not only could we define the speed of light as the electric field divided by the magnetic field,